So we're very happy to start with Eva Miranda, who will speak about B-Poisson manifolds to singular contact structures.
Thanks a lot for this invitation. This is my first experience. Of course, I'm using these days Google Meet and Zoom to teach online, enjoying this adventure, but this is my first experience for a talk. So it's very strange because I don't see all your faces. So I hope it goes well. I don't know. Cedric will send me WhatsApps if something is a disaster. I told him to do that. I want to thank the organizers. Well, I want to thank Anton to keep the flame, right? To organize this conference in the middle of this disaster, I would say. And that's the meaning of my little fish here. We are like these little fish confined in our house, which is these bottles, pretending that everything goes back to normality. I think that's good. Let's keep the optimism, and we hope that we come back to normal soon. Maybe we should keep this global Poisson in any case. In any case, this is my suggestion for a logo of the global Poisson webinar, and maybe also for the gum fishing this year. I also thank the organizers of the gum fishing. This talk is not the talk I was supposed to give in the gum fishing in May. But this has been like in April, but this has been postponed to next year. So I will give the other talk like next year. I hope that we can travel and we are all alive and feeling well, and then we'll meet in person there and we can even shake hands. And I want to thank very strongly my PhD student, my collaborator, Cedric Holmes, who has helped me not only, well, I'm going to talk about part of his thesis work, which is joint work, but I want also to thank him indeed to prepare the slides. This period has been very stressful for me because teaching online takes more time. So he even offered to help me, and indeed the last slides of this talk are indeed done by him. So I thank him. Partially done by him. So I really thank him. And he's there. We agreed that if something goes wrong, he just jumps and continues my talk. If we were in a normal conference, I could just give him the chalk. He would go on the blackboard and go on. But I don't know. We cannot do this. So let's go on. So what I want to consider today is some types of problems that maybe look a little bit far away from the Poisson context, but indeed have a lot to do with the Poisson context from the very beginning. And we will tackle these problems with tools indeed from Jacobi geometry. But you know, we will look at the problems we have. We can look from two different levels. We can look at them as Jacobi structures, or we can look at them as some singular forms. And this has a strong connection with the work that I had done a long time ago, and I have been doing with Victor Guillemin and Ana Rita Pires and Jonathan Weitzman and Jeff Scott, and that Marco is also working on. So it's a little bit, the idea is to apply those techniques that we developed to solve problems in dynamical systems. But first, we would like to understand topological constraints for these certain geometric structures that are going to have the singularities. And we are going to, well, first give a summary of what happens in the symplectic facet, and then look at the contact facet. And our goal is to find, indeed, topological conditions for a manifold, for a system to have periodic orbits. And in doing so, we will revise all material from several sources, and we will try to extend this. And keep in mind that our motivation comes from sometimes manifolds with boundary, and that this is a good setup for some problems in mechanics. So indeed, why do we care about periodic orbits? As Poincaré, we care because this is like the first place we can start understanding the dynamics. And I want to start really with a mechanical problem, with a problem in celestial mechanics. I'm going to consider the planar circular three-body problem. So the three-body problem is, well, I have this at home. I don't know if you can see it well. Well, this is a nice model of planetary motion. So if you think of planets, if you think of three bodies here, they are going to move, attract each one to each other, right? And if you want to look at the trajectory of one of these planets, then you have to take into account attraction of this planet with other planets, and so equations are complicated. Indeed, the three-body problem is not integral. But we could try to look at restricted versions that make sense for some practical purposes. For instance, the restricted planar circular three-body problem. What is this restricted planar circular three-body problem? We assume that one of the bodies has negligible mass. This could be the case of a spacecraft. And then the two other bodies move, of course, as an integrable system following Kepler laws. And then we assume that the motion of the smallest body is in the same plane as the other two, which are often called the primaries. So this is my motivating example. And this has a potential, okay, where this is the position of the Earth and the Moon, the QE and QM. Okay, I can assume that these primaries are Earth and Moon, for instance, and mu is the mass. Okay, so this potential is time dependent, and then the Hamiltonian is time dependent. The fact that it's time dependent, it's quite problematic. So sometimes it's convenient to change the rotating coordinates of the body. If you change the rotating coordinates, then the Hamiltonian becomes time independent, but you have a new term due to the Coriolis force, which is this term here. I don't know if you see when I put here. Can you see? Okay, that's good. So this problem,
sorry.
what?
The first term is still p squared, right?
Ah, yeah, sorry, typo. Thank you. This is a typo. Thank you. Okay, so we look, so this is p squared here. So we look at the critical points of the height function, and these are called the Lagrangian points. And well, this is a picture of the Lagrange points. Okay, so we may want to consider the periodic orbits of the Hamiltonian, of these Hamiltonian systems. And well, people in dynamical systems used a lot the perturbative methods and Poincaré continuation methods to try to look for these periodic orbits. And what I'm going to start doing is to present some results due to Frauenfelder and his collaborators, Alberts, Frauenfelder, Van Coort, and Patternet.
Sorry, one question. What does it mean, Lagrange points?
These are the critical points of H.
Okay, thanks.
Okay. So then what I'm going to present in the next two slides are results from Patternet, Van Coort, Alberts, and Frauenfelder, where they use tools from contact topology to address the problem of finding periodic orbits. Then we'll see where the singularities can come in. This is like a motivating example. So I'm going to recall here some basic stuff that if you consider a symplectic manifold and you take an hypersurface and you take a Liouville vector field of the symplectic manifold, meaning that you have such a formula, then if you assume that this Liouville vector field is transverse to this hypersurface, then you may consider the contraction of omega with the Liouville vector field, and this defines a one form. It turns out this one form is contact. It's a contact structure. And it turns that you may consider the dynamics and the red vector field equals the Hamiltonian vector field register. If you assume that this hypersurface is a level set of a Hamiltonian function, then the rep vector field of the contact structure, I'm going to recall basis in contact geometry in two slides, coincides with the Hamiltonian vector field. So there is Weinstein conjecture, which tells us that concerning periodic orbits, which tell us that if you have a contact closed manifold, then the red vector field emits periodic orbits. This is proved in dimension 3. There are different proofs, and well, there are some versions proved in higher dimensions. And well, here we are in which dimension, if we consider this problem, then the restriction to h equal to constant, it has dimension 3. Okay. So we apply this to the problem of the restricted three-body problem, and then you consider the fiber by h of a value of the energy of the Hamiltonian, sorry, of the energy that is below the first Lagrange point, okay? Indeed, it turns out that this has 3 connected components, and this is well known to Albers, Frauenfelder, Cohen, and Patternet. One of them, which corresponds to when the satellite stays close to the Earth, one when the satellite stays close to the Moon, or is it far away? Okay. Now, these 3 connected components, the interesting thing is to see what is their, do they have a contact structure? Well, it turns out that because this vector field here is, which is the Liouville vector field, is transverse, then applying the results of the previous slide, this is contact. One could try to apply here Weinstein conjecture, which is proved in dimension 3, but we cannot because it's non-compact in general, because precisely of the collision. So what makes non-compactness fail is the collision set that is called, what corresponds to really to collision. And what the authors do is to use Moser regularization. Okay, this is a change of coordinates, which is called Moser regularization. And indeed it's a compactification, because this allows to identify, if we take the connected component close to the Earth, this is going to be like a projective space. Okay, and then it can be checked that the Liouville vector field extends to this regularization, and then this regularization, this compactification is compact. So just by applying the results in the contact realm, Albers, Frauenfelder, Kurt, and Patternet prove that the regularized restricted, planar, circular, 3-body problem admits at least one closed orbit for each energy, which is below the energy of the first Lagrange point. Okay, now the questions is, where are those periodic orbits? Because of the regularization, of Moser regularization, these are not localized. Are they on the, what is the relation? Are they on the collision set? We would like to keep track of the periodic orbits, and we would like to know if singularities play a role. We will go back to this example towards the end of my talk, okay? And we will give a new collection of periodic orbits using our techniques that that complete the picture of former work by Marcel Guardia, Tere Martinez Seara, and Pau Martin. Okay, another example I promised in my abstract, I realized just this morning, because I think I have too many slides. So I'm just going to be very, very quick in this term. Just going to say that there are examples in fluid dynamics, okay, where the contact structure, indeed, where does it come? Well, if I consider Euler equations, which model the movement of a flow, okay, which is implicit. Okay, so I assume it doesn't have viscosity, okay, and I assume it's incompressible. The second equation is the incompressibility. Then the Euler equations, what they do look is at really model the dynamics of the fluid flow, okay, and out of this we are going to consider the stationary case, which is the case in which this term is 0, okay. And first, these equations, I've written these equations in the most classical possible way, which is an R3 with the standard metric. Of course, these equations make sense for any Riemannian 3-dimensional manifold. Indeed, they make sense in higher dimensions. And I just wanted to show just a very glimpse, very quick, a glimpse of these examples. It turns out that there is a very close connection to contact geometry, and this is known by works of Sullivan, of Ednar, and Reist, that if you consider a Beltrami field is going to be a stationary solution of these equations with constant Bernoulli function, okay? And a Beltrami field, you can, if you don't like to look at Euler equation, you can just think that it's a solution of these equations. It's a rotational, proportional to itself, of a vector field proportional to itself, and the divergence equals to 0. Okay, then Ednar and Reist proved that there is a one-to-one correspondence between, well, the class, between the class of non-vanishing Beltrami fields and red vector fields of a contact structure. Okay, and this is quite a classical result. So you have a connection between fluid dynamics and contact geometry in this game. What we did recently with one of my students, Robert Cardona and Daniel Peralta Salas, is to extend this picture of manifolds with boundary. So you can consider manifolds with cylindrical ends, and then close to the boundary, you can consider a model where you have a singularity. Okay, so these models, this kind of example. So this would be another situation in which, of course, it's interesting to know what is the dynamics and if you have periodic orbits in this setup in the case of fluid dynamics. However, I have many things to say about this, but today I think I will not come back to this example, and unless you ask me questions towards the end, because I think I have too many slides and I don't want to overwhelm with material. So that's a slide I promised where I explain really the only thing you need to know about contact geometry here is that, well, this would be like the symplectic and contact mirror. This is us during the confinement. And, well, we know what is a symplectic manifold, of course, and we know what is the relevant dynamics, Hamiltonian dynamics. If we look at the odd counterpart, then we're going to be replacing a 2 form by a 1 form, alpha, the 2 form omega. And instead of the condition of omega being closed, you are going to have this equation here, which of course makes sense because you are in a manifold of dimension 2n plus 1, and you are assuming that this is a volume form. This is equivalent to non-integrability, okay, of the kernel of alpha. And what is relevant, what would be the analog to the Hamiltonian equation, sorry, going one step forward, would be the two classes of equations, the red dynamics, which would be a red vector field defined by these two equations here, and also the Hamiltonian equations, which would be these ones. Today we're going to focus on the red dynamics, so on the flow of the vector field defined by these equations, which is a unique. Okay, so if I leave this picture in the lab, now I cannot because we are confined, so I have to stay at home. Then my PhD students, the day after, would do this. They would put a graffiti here where they would put B symplectic and B contact, like just as a graffiti. But indeed, this is what we are going to do in this talk. We are going to follow the idea of the graffiti of my PhD students. Like we're going to try to understand what is the analog of the B symplectic geometry or log symplectic geometry in the contact setup here. That's the purpose of my talk. And the motivation comes from these examples that I mentioned before. So, because I cannot go and see Sagrada Familia, I decided to put a picture and show you also my city here. This is Barcelona, this is Sagrada Familia. Some people like it, some people don't. And this is a nice picture where we can try to zoom in and zoom out and see different features of the city. And what I'm going to be doing is essentially looking at the structures that I consider, this what I call B contact, in both ways. Sometimes it's convenient to look at them as a Jacobi structure. Sometimes it's convenient to look at them as a singular form. And now I'm going to be very precise by what I mean by singular form. Okay, a singular form, I'm going to do the following. First, I'm going to place myself in an easy setup. I'm going to consider a manifold, and I'm going to consider an hypersurface, which is Z. Z here is an hypersurface. I didn't write this. I have a manifold of any dimension, I don't care. And Z is an hypersurface. And now I consider the set of vector fields that are tangent to this hypersurface. Okay? These vector fields is what we call B vector fields. Okay? I consider the set of these vector fields. Why B? Well, B comes from boundary, and all this slide and next slide is based on work by Richard Melrose, who used developed the apparatus of B calculus to consider the index theorem, manifolds with boundary. Okay, and okay, if I consider the set of vector fields of my manifold which are tangent to this hypersurface, the question is, are these vector fields sections of a bundle. Okay, and the answer is yes. Yes, they are sections of a bundle. And well, you can check that this is because they satisfy. I could try to construct this bundle with cocycles, or I could just try to see that the set of vector fields that are B vector fields, they generate a sheaf which is finally generated. Okay, and because it's finally generated, there is some result of SER in the analytical setup and in the smooth setup by Swan that tells me that I have such a vector bundle. So there is a vector bundle, and this vector bundle is called the B tangent. So the B tangent bundle is defined exactly dually by the set of by its section. Okay, the sections are the set of B vector fields. Is that clear? And any questions up to this point? If there are questions, just let me know. I don't know if I see here. Do I see? I don't see. Indeed, I don't see the participants. I don't see the blink if there are questions. So feel free.
I'll let you know if there are questions.
Okay, let me know. Okay. All right. So now we're going to play the B game. This is also the kind of work that Marco and his collaborators have been doing in the last years. We could dualize this bundle. Okay, we could consider the B cotangent bundle just as the plane dual of the former bundle, and then once we have this dual bundle, we can consider sections, okay, of any exterior power of this bundle. And this is what Melrose defines as B forms. These are going to be, so a B form of degree K would be a section of this bundle where P equals K, okay? And then you can extend the RAM differential to this setup, okay? And this is the way to introduce these singular forms, singular along this hypersurface. Once you have these forms, you can be very brave, and for instance, you can define whatever you want. You can define what is a B-symplectic form, okay? You can consider that a B-symplectic form should be, as the graffiti that we did on the former picture, should be complete analog to the standard symplectic case. Should be a closed form, okay? And instead of taking the RAM form, we take a B form, okay? So we take a closed form and we assume that it's non-degenerate in the same way we define to our students non-degeneracy in the symplectic case, okay? That we can always solve in a unique way, if you want Hamilton's equations, that we have, that omega defines an isomorphism between the B, the bundle and its dual, like the B cotangent and the B tangent, okay? So that's the way we could define B symplectic form. And in a way, what this point of view of defining B symplectic forms, that in a moment we'll see the connection to Poisson geometry, allows us to go very far, because we could think that everything that is done in symplectic geometry can be done with this new geometry. Well, this is not entirely true, but there are some methods that work very well. For instance, Darboux, you can prove Darboux theorem, you can prove B-Darboux theorem, and this is because the path method works perfectly, because you are in a way doing symplectic geometry over a different algebroid, which is this B cotangent bundle. Okay, in the same way we have played the even case. We could define what is a B contact structure, and we just take the former definition that we saw, and we think that alpha is a B form. And we could become even braver by replacing, we could follow this game also for other algebroids, and then obtain asymplectic or E-contact structures. The asymplectic structures were already known to Nest and Segan. Okay, so this slide is really a summary of, well, what you need to know indeed to follow the talk. Okay, we need to know that we have a generalization of the RAM forms, and that we take the definition of B symplectic or B contact form as a natural generalization to this new context. Then what's the connection to Poisson geometry? Well, indeed, B-symplectic structures are exactly dual to B-Poisson structure. So to have a B-Poisson structure or to have a B-symplectic structure is exactly the same. And what is a B-Poisson structure? And this is the same as log-symplectic. Well, with the difference that log-symplectic also includes the case of self-intersections. Here we don't assume that you have self-intersection. We have an hypersurface. So the definition of B-Poisson structure is, first, you consider an even dimensional manifold, okay, of dimension 2n, and you take a Poisson structure. Well, here I may assume that it's oriented or not. Initially, Victor and Ana Rita, when we started to work on this, assumed that it's oriented. We could also generalize this to the non-oriented setup. And then we just assume that the mapping that associates to each point pi n to the p is transverse to the zero section of this band. Okay? Then transversality gives me for free that the critical set, okay, it's a smooth hypersurface, which I will call from now on the critical hypersurface. And this is what is called a B-Poisson structure on the pair MZ. So to have a B-Poisson structure is to have a Poisson structure which satisfies this condition. If you think about this condition, if you take, for instance, a symplectic manifold, okay, and you take its dual, it's the bivector field of the symplectic form, then automatically omega n never vanishes. So this would be exactly allowing that omega n, well, vanishes or never goes to infinity. This would be allowing to omega n goes to infinity, but in a controlled way, okay, given by transversality. Instead of saying omega n goes to infinity, it's more practical to define this in the Poisson context. There is a close causing of this B-Poisson structure, which is folded symplectic structures, which were considered a long time ago by Victor Guillemin, by Anna Canas, and Woodward, and many other people. And there is a connection between all these structures that I will try to clarify in some slides. But let's say that the folded case would correspond to to define a folded symplectic structure, you don't need to consider a bivector field because you have exactly the same definition, but using forms. And then you assume that you have some kind of transversality condition, plus some extra condition concerning the rank that here you have for free, because what happens is that, how are these manifolds? Well, these manifolds are going to be indeed symplectic away from Z, okay? And along Z, indeed, Z, the critical hypersurface, it's indeed a Poisson manifold of this structure. And we can prove that if this hypersurface is compact, then this manifold is just a mapping torus, okay? It's just gluing the symplectic leaves, okay? And these symplectic leaves have codimension 1. So we can say that we understand quite well geometry of these manifolds. This is like a summary. This has been studied by several people. I cannot cite everyone. Please consider yourself cited. So what is the situation, right? We have this BM symplectic. Well, here I put M. This would be a generalization. I could take a generalization of this definition by considering that something vanishes up to order K, okay? And then I would have higher order singularities. This is what Jeff Scott did in his thesis, and he worked out the picture to generalize this to higher order singularities, okay? So you may consider that your local normal form of your symplectic structure, so the Darboux theorem, is 1 over x to the m, x1 to the m, dx1, wedge, dy1, plus standard Darboux structure, okay? Then you have like these several categories that you want to understand because they look very close, because you can play the same kind of games. You can prove Darboux theorem, you can extend forms, you can do many things that are close. Indeed, as examples, you have Darboux theorem, you have some Dolzan convexity theorems that we proved in the B case with Victor and Arita and Jeff, and in the BM case also with Jonathan Weitzman. And also we have some action angle coordinates. This is something that in the B case I did a long time ago with Anna Kissenhofer, a former student of mine, and that can be sent to the folded setup. This is what we did with Robert Cardona. So we have, like, this picture wants to show that these manifolds resemble quite a lot. So we want to see, are they the same? They are not the same. And the following result, we wrote it down in 2015, and it's a very nice idea of Victor and Jonathan that we did together, the three of us, that what it does is to associate, when you have a BM manifold, indeed you can in a way desingularize it. So this defines the notion of this desingularization of BM forms. And it turns out that there is a difference according to the parity of the degree of M. If the parity is even, then you can associate a family of symplectic forms, okay, that coincide. You can imagine that you have a neighborhood of your critical set, okay, and in a way you change in this neighborhood of your critical set your BM symplectic form to an actual symplectic form. Indeed, that's what you do. And you do this by stretching. So this family of epsilon is done by stretching this neighborhood. And that's a theorem that clarifies quite a lot this relation between these three boxes, okay? Because it tells you that, okay, you may have a BM symplectic structure on your manifold, but you have a way to associate to this structure a family either of symplectic forms or a family of folded symplectic forms. And that the behavior depends exactly on the parity of the manifold. So indeed, I enjoyed very much working on this. When we found this out, we thought, come on, why didn't we understand this before? This just happened in 2015, but this is one of these results that you say, of course, why didn't we think about this before? This clarifies in particular topological abstractions, because as a corollary, if you have a B2K symplectic manifold, then automatically this manifold is going to admit a symplectic structure. And in the odd case, a B2K plus 1 symplectic manifold is going to admit a folded symplectic structure. But the converse is not true, okay? So, of course, you may have, like in both situations. There is a very nice paper by Gil Cavalcanti where he does examples and counterexamples of this story. And in particular, easily, if we take S4, of course, S4 cannot admit a B-symplectic structure because of the same reason it cannot admit a symplectic structure. You can just make the same proof, okay? The proof that we do to our students to check that the symplectic form, that the class of the symplectic form cannot be zero on a compact symplectic manifold, works also for B-symplectic manifolds. There you need to replace the RAM cohomology by the cohomology associated to these B forms, which I didn't talk about because it's not the purpose of this talk, but it's called B cohomology. Okay, so of course from this very same proof, which is Stokes' theorem, you obtain that S4 cannot have a B-symplectic structure, but it has, of course, folded symplectic structure because any four-dimensional manifold admits folded structures thanks to a result by Ana Canas da Silva, which uses the H principle. Okay, so this means that this folded structure that you can put on S4 cannot be on the image of this deblogging. Okay, so you have, in a way, like three boxes. If you want to organize your apartment during the confinement, this was my first idea, but the apartment is not organized. You see a whiteboard just to hide whatever is behind the wall. So if you want to organize these structures there, you have BM structures, okay, and you can deblog them. So the blogging gives you a way to take things from the BM box and put it on the symplectic box. And then you have, it gives you a way to, if M is odd, then you put it in the box of folded symplectic. But this box, if I put all the things of the folded symplectic, the boxes are smaller. I have folded structures which are not in the image of the debloging. And this is interesting to understand what are the constraints for this debloging to have an inverse. And there are some topological constraints. For instance, in the neighborhood of a torus, you can go back. That's very interesting. But I'm not going to talk about this. And these observations are relevant if you want to study, for instance, KM theory for these manifolds. If you want to study integrable systems, action angle coordinates for BM symplectic manifolds, one of my students is finishing his thesis on this sort of topics and using these ideas. So it's like a whole, it's quite interesting to see this. But now I want to see another general picture, and because you cannot come to Barcelona, I show you one of the favorite images of Marco of Barcelona, which is, I didn't know that you were my chairman. It looked like I knew that this is the inside of Sagrada Familia. So now we are inside of Sagrada Familia. We are confined inside Sagrada Familia, but we look up, and this is what we see. If the light, if you enter there and there are not a lot of people, and that's what you can see. So now I want to look at these B contact structures in the same way that we have that B symplectic are Poisson structures. I want to look at the B contact analog, and this will be Jacobi. This will come from Jacobi geometry. So it makes me very happy to see that Jean-Michel is here. So that's a picture that I explained so far. We have symplectic inside a box of B-Poisson. Okay, here I'm assuming this box is like, okay, there are comments I could make about these boxes. And Poisson. And here I have contact. Now I want to find the boxes that contain the contact. So of course, a big box that contains everything is Jacobi structures. So what are Jacobi structures? So here I put some pictures of people who contributed to the topic. Of course, not everyone is here. We have Lichnerovich, we have Kirillov, we have Paulette Lieberman, who is the third on this slide, and we have Jean-Michel Marr, who contributed a lot to this theory. And I'm just going to put really a couple of slides on the theory. So we can generalize the notion of Poisson bracket to that of Jacobi bracket, okay, in which instead of associating a bivector field, we associate a pair of bivector field plus a red vector field, okay, well, a vector field. So we associate a bivector field and a vector field, satisfying these two integrability equations. And this has been studied long time ago, and there are many, many results in the theory. And I just want to give the definition of B contact from the point of view of Jacobi. I want to, in this big picture, so if I look up at Sagrada Familia, I want to understand how I can put the box of B contact inside the box of Jacobi. First, it's good to have some trivial examples. Like it's easy to see that Poisson fit there, because if you declare that this vector field is 0 in the pair, then you get exactly the Poisson bracket from the former slide, and you can get exactly the Poisson bivector. Contact manifolds, of course, are an example of them, okay, where you can define the rep vector field from this equality, and also locally conformally symplectic manifolds. This will be manifolds, okay, where you have that omega, that the two form, you have a two form and a one form. And omega is not closed, but the differential of omega, you can write it as omega wedge alpha, where alpha can be chosen to be closed. And these are called locally conformally symplectic. And they are relevant indeed to our work, but I didn't say this, I should have said this at the beginning, that what I'm explaining is written down, but the version that you have on the archive doesn't correspond at all to the version that I'm explaining. Indeed, there is a paper on the archive from a long time ago, but Selvik and I decided to add much more stuff. So finally, there are two papers that you can find now in my web page. I hope that they are already in my web page, because to update my web page, the update of my web page uses a very strambotic a computer program, and this is because not because I mean this web page, I didn't do it myself. One of my postdocs did it, and he's very, very good. So it takes like 10 minutes to update. It should be there already, the 2 papers. The version that we wanted to post it on archive today, but it will be there next week, I hope. And we will post the 2 papers. So one of the papers concerns the general theory that I'm not completely explaining, because I'm not explaining that there is a Darboux theorem, that there is a symplectization, blah, 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 blah. And another one which concerns the rep dynamics. Okay. So what I'm explaining now in these slides is in the first paper, but you can find it on my webpage, and I think also Selvig put it on his webpage. So, okay, what is the definition of B Jacobi? Because if we have a definition of B-Poisson, we should have a definition of B Jacobi. Okay, so if I take a Jacobi manifold which is odd dimensional, okay, I say that it's B Jacobi if you have this transversality condition here. Okay, so the transversality condition, you need to take to wedge n times the bivector field, and then you add the what I call the red vector field, okay, of the Jacobi structure. And then you can, once you have this definition of B Jacobi, then it's very easy to prove that there is a one-to-one correspondence between B Jacobi manifolds and B contact manifolds. Therefore, you can really put the B contact inside the Jacobi box. Okay, so that's the very basic thing. And of course, now here, the question is, can you do symplectization? Can you prove a Darboux theorem? You have Darboux theorem, but you have several models. All this I'm not explaining. I'm going to focus just on 2 results. Indeed, I'm going to be late. Okay, I hope that I can do this quite quickly. The first one concerns this obstruction theory. So, natural question, if you have any odd dimensional manifold, can you put on this manifold a B contact structure or a BM contact structure? That's the first question I want to answer. And the second question is, can you go back to the first example that you did, the restricted 3-body problem, and solve it and give some new results on periodic orbits using the B contact? And the answer is yes. So I'm going to try to answer these 2 questions. So the first, I'm going to try to prove that on any odd-dimensional manifold, I can put a BM contact structure. So I'm going to strongly use the tools developed by Borman, Eliasmer, and Murphy to prove the regular case. So if you have a 3-dimensional, it was known already to Martinet and Lutz that any 3-dimensional manifolds are contact, and then in dimension 5, this was generalized by Roger Casals, Francisco Presas, who is here, and Pancholi, in dimension 5 by proving that any almost contact, you needed some additional topological condition, which is called that the manifold is almost contact, that you can look with some Chern classes. Okay. So this is what they proved in dimension 5, and they did it by very ad hoc techniques, and then Borman, Eliasmer, and Murphy proved the general case, maybe 2 years ago, proving that any almost contact closed manifold is contact. And they did it using a DH principle. Okay, so what we want to do is to prove the same, but we are going to take advantage of the fact that they already proved the contact case. And we are going to go back to this idea of desingularization and singularization. So now in the case of one forms, it turns out that the picture that we did with Victor Guillemin and Jonathan Weizmann is easier for one forms. And for one forms, it's very easy to go both ways. I'm simplifying a little bit. But you can, in a way, if you have a contact structure, there are ways to singularize this contact structure. But you need some conditions. So in particular, with Selvig, we proved that for any pair of contact manifold, and so if you already have a contact manifold, that now you know what the constraints are, which is the almost contact condition. Then if you take a convex hypersurface, convex, it means that the Lie derivative, that you have a contact vector field transverse to it and in the same direction. Okay, so this is convex hypersurface. contacts. Then you can prove that there exists a B2K contact structure having this convex hypersurface as critical set. You may ask yourself how generic is to have a convex hypersurface. We prove this in any dimension, but then it turns out that in dimension 3, okay, the condition is of being convex is generic, because you do prove that if you take if you take a surface, you can always deform it to make it convex. So in particular, as a corollary of this result and Giroux's observation, for any three-dimensional manifold and any generic surface, there exists a B2K contact structure on M, realizing Z as the critical set. And the idea is to singularize, okay? So the idea of the blogging or the singularization that we did with Victor Guillemin and Jonathan Weisman was to make our life easier. And now we want to make our life more complicated. But let's say we start with existence of contact structures. And then if you have a convex contact structure, you are not going to have this nice contact structure here. You may have a function multiplying, but you can choose a contact structure of this sort, and then you can singularize to put the singularity here. So you singularize by a transformation that in the limit will give you a singular contact structure. That's the way we prove that you can always realize this set as a critical set of a contact, of a BM contact. And in the odd case, you can do the same. Well, you have a problem of parity, because the number of components that you need, of your construction needs, what you can let's say you can prove that you have a contact structure with components such that one of the components coincides with Z. That's the result we have. So you have existence. So you don't have, let's say, the only topological obstruction is the one of almost contact. It's the same as in the contact business. Okay, now what about periodic orbits? By the way, this is Cedric before cutting his hair. And this is the lab when we were not confined in our houses. Let's go back to the initial computation, the planar restricted three-body problem. And we go back here. I have already corrected the typo that Anton observed. And that's the Hamiltonian, okay? And the vector field here that we consider the Liouville vector field is this one, okay? Then this vector field is transverse to sigma, okay, to the level sets, and that's the first thing. That's the first lemma. And then the thing is that one thing we need to introduce a singularity, okay, somehow, and we do this not because we want to introduce a singularity. We put this equation here that, of course, it's going to give us a singularity. This comes from the literature, because classically, McGehee, who has been working in this problem for a long time, and several problems in celestial mechanics, introduced this change because it's a way to take what they call infinity close to the zero, okay, which is what happens here. But people working in this field were never considering working at infinity. They were always close to infinity. So indeed, if we do this change, this transformation change, we get this symplectic form that is not symplectic when x equals 0. It's B3 symplectic. So it's one of our guys. Of course, people working in celestial mechanics, when they got here, they say, oh, you get something that is very close to symplectic, but it's not canonical, blah, blah. It's a Poisson structure. That's what it is. And we are Poisson geometry, so we can use the power of Poisson geometry to solve these problems. Okay. And okay, now I want to show indeed how to use the ideas that we developed in the B contact realm. So what I do is to take a level set of H, and I want to see if this level set is become B3 contact, okay? After this McGehee change, of course. That's a computation. And it turns out that, okay, it's wonderful. This vector field is everywhere transverse. So now you contract the vector field with omega, and this is your candidate for V3 form. Okay, what makes me unhappy here, the Frony, is telling me why am I happy? Oh, the critical set is a cylinder, highly non-compact. But it turns out, so indeed we proved, I changed a little bit the order of the slides, sorry. We proved a result more general that it's what we call like our naive B-Poisson conjecture in the B case, that if you have, if you consider a compact BM contact manifold, okay, or so we just need that the critical set is compact, then the red vector field admits infinite number of periodic orbits. This is something we can simply prove using Jacobi analysis, because checking that the restriction in the three-dimensional case, the restriction to the critical set is just a symplectic form, and then just checking out that you have a vibration by S1. So you get infinite number of periodic orbits. But in this case, we cannot apply this general result. So on the 1st of May, the day of the workers, Cedric and I decided to solve this problem. And I said, it has, Cedric, let's prove this. We were sitting down, it's one in our houses, and by Zoom, we computed everything. And that's the computation we did, okay? That's the computation. So we computed the B form. The B form is of this sort. That's the B3 form. That's the contact structure, okay? And indeed, that's the critical set, okay? So as it's very easy to check that when you are, thanks to Jacobi, to the Jacobi point of view, is that the red vector field is just a Hamiltonian with respect to the restriction. So it's just a Hamiltonian with respect to the PR. So if you look at this cylinder, which is generated by the PR and the P alpha in the previous slides, which is, okay, it's a, let's think that they are polar coordinates, then what you get is just a vibration. Well, it's not polar coordinates, it's the coordinates on this cylinder. Then you just get this vibration by S1s, and all these are periodic orbits at infinity of the restricted free body problem. So we got this result, and we spent like the last week trying to check with our colleagues in celestial mechanics whether this was known. Apparently this is not known, though it makes sense, let's say, with the results that they get close to infinity, in which indeed you have an approximation like the two-body problem, which you know it's integrable. Therefore, these circles make a lot of sense. Okay, and okay, that motivates like what is going to be the analog of B-Poisson's conjecture in the singular setup. In the regular setup, it was the red vector field admits at least a periodic orbit, and we want to prove this in the three-dimensional case. Okay, let's go back to this point of desingularization, this idea of desingularization, or the blogging that we started with Victor and Jonathan, and it works very well in the contact setup. Then the desingularization provides, instead of a family of Poisson structures, it provides for you a family of bivector fields of the Jacobi structure, and you can check their convergence, okay? So you can prove that you have a family of contact forms that converge to an actual contact structure in the even case. In the odd case, you get, of course, this kind of folded contact that I'm not going to talk about, okay? In particular, but the big question here, like, first you get, okay, Cedric, that's it, we have the proof. You have this family of periodic orbits, but why are they going to converge to a periodic orbit? Maybe they won't converge to a periodic orbit. Let's think a bit how you think of these periodic orbits in Rabinovich variational point of view. You can always identify the periodic orbits with the critical points of the action functional. So indeed, what we would like to do is to take the limit where epsilon goes to 0, but the problem is that this family of orbits need not be continuous. Okay, you have that this is the action functional associated to this family of contact structures that desingularize your structure, and you are working here in the loop space, but this assignment is not necessarily continuous. So what you can say is that if this family is away from the critical set, then you are going to have periodic orbits. But if it crosses the critical set, or if it's inside the critical set, you cannot conclude from this proof. So attacking BM-Weinstein conjecture is the title of this slide, because this is what we did to attack it. And it turns out, surprise, that in the three-dimensional case, because of this observation that the Hamiltonian vector field, that the red vector field is tangent to the critical set, and the critical set is two-dimensional and symplectic, and this red vector field is Hamiltonian, then you get for free that if the critical hypersurface is compact, then you have infinite periodic orbits on Z. So that could be the first, let's say, BM-Weinstein conjecture, okay? But first question, can you prove? The difficult thing is, can you still get periodic orbits away from Z? Counterexample, take S3, take this Liouville vector field, take this rep vector vector field, and then take the critical set S2. And inside S2, you have periodic orbits, but away you have no periodic orbit. So you have examples without any periodic orbit away from Z. This got us very nervous, and we decided to go to the classics. So we decided to go to Hofer. So what I'm going to explain now is very quickly that in the regular case, there is a whole theory of contact topology of classification of contact structures in a way. They say there are like overtwisted, and there are what they are called tight, okay? And overtwisted, let's say from a mechanical point of view, if you want that, let's say, of course, you can always relate symplectic geometry to contact geometry and BM to contact geometry through the symplectization. But if you want a compact result, a symplectic manifold, such that the boundary is this contact object, then overtwisted are not nice because they are non-fillable. So overtwisted, let's say they are a delicatessen for contact geometers, just to say it very quickly. So we decided to go to the delicatessen, and what is an overtwisted contact structure in dimension 3? We just did dimension 3, higher dimensions. The definition was developed by Niederkruger and also in this paper by Bormann, Eliasman, and Murphy. And okay, a contact structure is overtwisted if you have a disk such that the intersection with the contact structure has a foliation of this type, like a sphere. Okay, and a contact manifold that is not overtwisted is called tight. For instance, the example that we saw before, the example of the planar restricted three-body problem is tight. Okay, so Hofer proved that if you have a three-dimensional manifold, okay, and you have a closed overtwisted contact structure, you have periodic orbits. So he proved Weinstein conjecture, assuming that you have an overtwisted disk somewhere on your manifold. Okay, and he did this using the symplectization and using holomorphic curves. That's the way. So he did this using analysis. So what we did with Cedric very recently is to adapt these ideas to the BM context. And to summarize, let's say they work well, and in a way, a result which is not true, by the way, is that you need really these manifolds to be closed, to be compact. So if you think that you just take out the critical set, this is not going to work. But what you can do is to adjust when you get to the critical set. In a way, the idea that we do with Cedric is to assume that you have some invariants close to the critical set so that you can write your contact structure in this way. Indeed, this works not only for BM contact structure, it works for any contact manifold, okay? For any contact structure, or for any structure which is contact away from a set, and such that you have a vector field which is transverse to the components of this critical set Z. Okay, then you can prove, well, here we stated for closed BM contact, then you can prove that you have two situations. Either you have a periodic orbit in M minus Z and away from Z, okay? Or you have a family of periodic orbits that converge to the critical set. Indeed, and these periodic orbits are contractible loops in the symplectization, because the idea of Hofer is you go to the symplectization and you look for planes of finite energy, okay? And you prove this and its analysis, okay? So indeed, we could prove more. We could prove that if you have a contact manifold such that is overtwisted away from a set that you can think that can be the singularity of this generalized contact structure, then we prove that there exists a one parametric family of periodic rep orbits in the R plus invariant part, or a periodic rep orbit away from the invariant part. So the mantra is that non-compactness plus this R invariance leads you to compactness. And what the question we still want to understand is applications of this theorem. And I'm over time. I think that I've been speaking for a long time. So I'm going to close with a final question. We have proved that you have infinite periodic orbits on the critical set. We provided examples that you don't have periodic orbits away from the critical set. And we proved that if you have an overtwisted disk, you have periodic orbits away from the critical set. But maybe the good singular Weinstein conjecture should also admit singular orbits as below. So this would be the picture corresponding to this identification of B contact with contact manifolds with boundary. And then you want to understand, if you have a Hamiltonian system, if you can have dynamics that go to the boundary. This is interesting, especially for the problems in fluid dynamics. Or if you could have such a picture. So maybe the singular Weinstein conjecture that we couldn't prove yet is that if you have a compact VM contact manifold, there exists one singular periodic orbit away from Z. That's what we want to prove. And of course, what are the difficulties? We started to think about this, and with this I'm going to close. And the difficulties is that if you want to do this using the apparatus of contact geometry, of contact topology and symplectic topology, you need to understand these periodic orbits as, in the variational sense, as critical points of your action functional. And then what happens is that you need to enlarge the loop space, because you want to consider orbits as such, which are going to be heteroclinic, and that from a smooth point of view are the union of four orbits. You want to look at this union of four orbits as just one single orbit. So you need to change the loop space. And of course, this is maybe the first step towards what would be a Floer theory for these Poisson manifolds. And I think, I'm sorry, I went over time. Thanks a lot for the ones who survived to this point. That's the end of my.
Okay, so if you would like to ask a question, please raise your hand, or maybe put a little comment into the chat. While you get that ready, let me ask a question to begin. Can you go over the for the restricted three-body problem? What these Reeb orbits, could you give the interpretation of these results in that example, just like a summary for that problem?
Yeah, you mean the results that we obtain in the yeah. So the interpretation is very simple. I can go back to the slide, or I can do it with my hands. You have, or I have my whiteboard here. So you have this three-dimensional manifold, and the critical set is two-dimensional, and it's symplectic. So what happens is that the red vector field of your contact structure is going to be Hamiltonian there. So this is not in the restricted three-body problem. This is not good enough, because the critical set is non-compact, so it's a cylinder, so you cannot conclude. But you do explicit computation, and it turns out that what you get is that the Hamiltonian is just the height of the cylinder, in a way. So then you get automatically, you have a total control of what is a symplectic form, and you compute, and you have that the Hamiltonian is just the partial of theta, in a way. So the interpretation from celestial mechanics is the following, that when you are close to infinity, it's well known to people working in celestial mechanics, well, to people working at least in this kind of problems, that when you are far away from your primaries, you can think that your problem, because you have rotating coordinates, so you are moving out one of the bodies, that your system is somehow two-dimensional. It's like a two-body problem. But this is the system that you have not on infinity. Then you are adding, you're in a way completing this picture, and you add infinity. So in a way, you are projecting your system to a two-body problem at infinity, and a two-body problem is integrable.
Does that mean that these trajectories are basically treating the entire system as like a point mass, and you're just very far away?
Yes, exactly.
I see.
Exactly.
I see. But you say that you see this trajectory in the completion. It's at infinity.
Exactly. So it's not, let's say that we were like for a week with Cedric and Amadeo and these people who work in celestial mechanics, trying to see if it was trivial to see that you get those, but you don't get those because you get a different, this system that you are describing is not at infinity. So what we are doing is to prove that at infinity you have a completion of these periodic orbits. Indeed, there is a recent result by, well, not so recent, it's maybe 2017, that Marcel Guardia and I'm going to forget, Tere Martinez-Feara, and they are all in my department, this is great, and Pau Martí proved that you have a horseshoe in the regular part. Therefore, when you have a horseshoe, you know that you are going to generate periodic orbits, okay? And then because of this horseshoe, you have periodic orbits, but these periodic orbits that they describe are not at infinity, okay? So, but let's say it fits, the explanation is that it fits, but it's a computation finally. It's like putting your hands in the formulas. It's like this exercise that you leave to students to do, and when you do, it works. It's like very simple computation, but it's
okay. Are there any other questions? Any of the? I see that there's a bunch of celestial mechanics here. Maybe they have some questions. Experts. I have one more question. So can you go back one slide?
Back one slide here.
Yeah.
So you want these singular points. Yeah, sorry, this one.
Yeah, so you said something about changing what you mean by loops.
Ah, I said it here. Well, I mean loops, that here this gamma is a loop.
Yes.
It's a mapping from S1. So the thing is that classically, there is a correspondence by Rabinovich that gives you a one-to-one correspondence between critical points and periodic orbits. This works in the contact and symplectic setup, and it's a computation. And then the thing is that if you want now to find solutions, so the critical points of this function are going to be these loops, and these loops are smooth, so are perfect circles. But now you want to twist this definition, because if you want to include a solution heteroclinic orbits, you need to change the loop space. And
what do those limiting? So when you
need to consider manifolds with corners, and you need to consider like mapping of some. But the thing is that we started to look at this, and there is not enough information, let's say, of people who studied the loop space when you have points. So you have like a loop, and then you fix a finite number of points, and then you look at, let's say, things that are smooth, but just away from these points. That's the kind of space you need. And we didn't find people working in the analysis of these loop spaces, because what you need is to be able to prove that there is a one-to-one correspondence, that there is a variational principle. So you need to understand that the analysis of the space of loops, and first you need to define the loop when you have a fixed orbit. So from a topological point of view, this has been studied, but not the analysis. You need to define like something that is smooth by piecewise smooth mappings. So I don't know, that looks quite scary, essentially, especially for Cedric, who's at the end of the thesis. So this is maybe the beginning of a new thesis, indeed, of another thesis, not the one of Cedric. The Cedric one of Cedric is over.
Okay, any other final questions? I see there's many thank yous in the chat, but does anyone have a question? If not, let's thank Eva one last time.
Thank you.